Okay, so let's continue then. Before I continue, any questions? Is it more or less clear what the strategy is? I mean, okay, it's not clear at all why saying something about zeros of this function not being in certain lines should have anything to do with primes. But at least it should be clear that you know how the Riemann hypothesis is improving over things that we're trying to say here. Right? Okay, so now this is I think it's called 4 in the paper we're following. Okay, so let me use that numbering. Okay, so we're going to prove is that zeta, I keep writing size rather than zetas. Zeta is not 0, right? And this other function, right? This phi s, once I remove the pole, right, it will also have a pole. And it turns out to be of residue 1 as well. Is holomorphic, or you know, holomorphic, or you know, analytic, or extends analytically for the real part of S bigger or equal than 1. Okay. And in a way, I mean, the Riemann hypothesis is saying that this is true all the way to this critical line of a half, right? Basically, the Riemann hypothesis says that this is true. Essentially, we'll see in a second, this is true for replacing this by just bigger than a half. Okay, and then I'll say a few words about what that says about the prime number theorem. Okay, so let's prove this. Okay, so let me just mention that you know the original proof of this, I think by Vallée-Poisson, it was very long, lots and lots of analysis, and we're going to do now actually is it's relatively simple. I mean, right? There's been 100 years for cool tricks to be developed, and yeah, so it's a lot simpler. So okay, so first of all, for let's look at where the problem is easier, which is in where the real part of S is actually bigger than 1, right? Because we're in this line, right? This is the line real part of S equals 1. Over here, where it's bigger than 1, we know exactly what the functions are. We have this product formula, the sum formula, everything, right? We know that they're extendable, at least the zeta function, up to exactly on the line. We have to be a bit careful on the line, but outside of the line is fine. And so let's start with outside of the line. Right? So for real part of S bigger than 1, right? Then of course the product formula, right? The product formula, you know, with the Riemann zeta function is equal to the product of the 1 over 1 minus p to the minus s. The formula guarantees, right, or implies that that the real part of that the zeta function outside of the line is non-zero, right? Okay. Okay, so I'm getting questions about the Riemann hypothesis. Yes, okay, so this is a bit far from what I usually think about, so I don't know exactly what's known and not. My guess is that probably none of this is like all questions of this type, the answer is we don't know. I think, okay, and now I'm not sure. You know, this is something that it's a bit outside of what I usually think about, but I think, I remember reading somewhere that okay, so basically the question is what's known about another way of formulating the question is what's known about if zeros were to exist, right? So basically, okay, so let me go back before we do a bit more math and answer some of these questions to the best of my ability. And if there's specific questions, I can definitely go and look into it and ask colleagues. And on Friday we can talk more about it and I can be more informed. But the it's not so hard to show that all the zeros, besides that there's some trivial ones in some negative integers that just comes from the functional relation to map it to the negative real part. That's not really that interesting. The interesting zeros could potentially lie between the real part, basically 0 and 1. Right, and we're only looking on the right side of this critical line, so let's focus just there. Okay, so on this red region. And now you can ask, okay, what do we know about locations of these zeros if they exist? So I would guess that we know that they cannot possibly have small, like imaginary parts, because otherwise we would have found them, right? I'm sure there's ways of like looking for the zeros, and no one has found any. Now, if there's proven upper or lower bound, so I believe, I'm not sure, but I think that if you can show that the real part of any zero is, say, smaller than 0.99, then I think there's a way to push it essentially all the way to the Riemann hypothesis. I think getting that there's no zeros in even a little band around 1 is already basically gives you the Riemann hypothesis. And if it doesn't, it would still be a major result, because basically, okay, this is an aside, maybe an aside important to say, right? So when you say essentially what the Riemann hypothesis tells you is that, you know, when you have that the number of primes from 1 to x is something like x over log x, right? You can ask now, okay, but what about the deviations from this, right? So this is equal to x plus some kind of error, sorry, x over log x. Okay, this is getting all. Like, plus some kind of error, right? Let's say, right, some kind of deviations. And you can ask now, what is the size of these? What are the size of these deviations, right? And basically, what we'll show is that this is right, is smaller than is little low of x over log x, right? Where little low means that, you know, once you divide by it, it goes to 0, right? Now, it turns out that if you show that there are no zeros, right? So if you show that there are no zeros, like no, let me write it here, that if you show there are no zeros with real part of S bigger than, or maybe bigger or equal, probably bigger. Yeah, bigger should be enough. Let me look back. Yeah, let me say bigger or equal because I'm not sure. No zero is bigger or equal than some beta, then this basically implies that this error is bounded by, you know, by something like, is say O of x to the beta, okay, and maybe some log factors, right? So in computer science, you use like O with a little tilde if there's hidden log factors, okay? I'm not sure if there are or not. But so basically, if you're able to go, like all we know is that the error, like that the number of primes, the prime counting function looks like x over log x, and there'll be some deviation from this. Right? All we know is that these deviations are of lower order than x over log x. But if you had the Riemann hypothesis or any improvement over this statement that there's no zeros in the line of real part equals 1, if you could go all the way to say 0.9 or something like this, then you would effectively get a much better control of the error of the prime number theorem, right? You would get some theorem like, you know, you would get some, let me write it here, you would get some theorem that pi of x would be equal to x over log x plus or minus something that looks like x to the beta. And now, you know, I don't know how much probability you've taken, but if you have random variables, right, say, if you think of the primes as being random, like they have a certain density, right? They should be up from 1 to x should be roughly x over log x, right? So their density of a certain size should be roughly 1 over log x, right? So if you think of them as random, the probability that you see a prime, if you look at the number x, should be roughly 1 over log x. Now, if you've seen things like central limit theorem or just compute, you know, the variance of the number of heads if you flip n coins, right? Then the standard deviation of these random variables and sort of size of the fluctuations are always of square root of the number of random draws. And so if you believe that, you know, prime numbers behave randomly, condition, of course, in having this certain density, but that otherwise they are very random. Then the right answer should be that the deviations, right? This deviation factor should really be a half, right? Because if you think of flipping coins, this is exactly, the fluctuations are of psi square root n. And so this is really, in a way, this is the Riemann hypothesis, right? That the primes behave randomly in this sense, right? But even getting, 0.99 rather than a half, this is not known. And I think I even saw somewhere that if you get 0.99, it's possible to push all the way, but this I'm not sure. Did this answer the question? Yeah. So this is what, this is one way of viewing the Riemann hypothesis. And there's many things in analytic number theory that are exactly about proving that primes behave randomly in different senses, right? Many of which use sometimes condition in the Riemann hypothesis actually, right? But there's many other conjectures, many really amazing results in number theory that are all about trying to argue that, prime numbers sort of behave randomly. Okay, I mean, I could talk about this for a while, but maybe I shouldn't. Let me just say, for example, my own interests, I've dealt in the past with derandomization. So sometimes you have to come up with, you devise some kind of algorithm to solve some kind of task. And it's easy for whatever reason to devise algorithms that are random. They have some randomness in it. Maybe one way to think about this is that if you're trying to analyze your algorithm in a worst case type way, then if your algorithm is random, sort of the worst case can't be too planned against you. I mean, I'm being extremely hand wavy, but sometimes you want to make choices in your algorithm that almost all choices work as long as they don't satisfy some bad property. But it's actually extremely hard to find deterministic constructions that you're absolutely sure won't satisfy this. And so this derandomization is often a very difficult problem. But actually, one can use number theory to solve this sometimes. Right? And I mean, this is sort of how the first expander graphs were built, and so on and so forth. Right? Is the idea that you can use this fact that when you try to understand, let's say, primes or number theory behaves randomly, you learn a lot about number theory, but then it means also that you can use number theory to devise algorithms that before you only knew how to do with randomness. And that side is something that I've been interested in the past. Okay, so this was a long answer to a short question, but it's a very interesting point to make. So I hope this is enjoyable. Is there any other question? I mean, these last lectures are meant to be a lot more informal, so happy to stop and talk about whatever. Okay, all right. So let's see where we were. So clearly for RS bigger than 1, then the product formula implies that there's no zeros. Okay, so far so good. And now what we're going to do is we're going to relate phi of s to the logarithmic derivative of zeta of s. Right? So that zeros and poles of zeta of s will be poles in phi of s. And by showing that phi of s has no zeros, you're showing effectively that phi of s has no poles. And so the Riemann hypothesis can be formulated as phi of s having no poles and therefore being analytically possible to analytically continuate. Okay, so let's do this. So we have also that, right, for again, let me go back to the for real part of s bigger than 1, right? Let's look at a logarithmic derivative. Yeah. Okay, let's put a minus sign because this will be nicer. Okay, so this is now a bit of a nasty calculation. Let's try to do it together. Okay, derivative. Okay. Maybe I should say instead here dds. Otherwise, it looks like I'm just doing to the power 1. Okay. Okay, now we take the derivative. I mean, we've taken these derivatives many times, right? When we have, remember what we use the logarithmic derivative for. right? We said that if a function had zeros of certain orders or many zeros, that you could write it as basically, ask x or z minus a zero times z minus another zero times z minus another zero and so on and so forth. And when we took the derivatives of the product divided by the product, then basically shows up a sum where there is one term per factor in the product. And that term is very easy to see what it is, right? And it's exactly the kind of thing that shows up here. So let's work that out. Right? So now you have the derivative of this, the derivative of the product is just you take a sum where you differentiate each one at a time. But now you're dividing by the product, so all the terms that you didn't differentiate will get canceled out, and you just get the derivative of the one term divided by the term itself, right? And so what we have, okay, so now I'll just write this down. I've already done this calculation, and we can just look at it. I mean, there's no point in spending 15 minutes trying to work out this derivative and make sure there's no errors. Okay. Right, this is just the derivative of 1 minus p to the s to the minus 1. And right, the 1 over p minus s to the minus 1 becomes 1 over p minus s to the minus 2, and then you have to differentiate what's inside. Right? And you have to divide again by this term. Okay. And now, okay, is this clear? I mean, this is something you just need to work out, but this is just the derivative of the term, right? 1 minus p minus s minus 1, right? Divided by 1 minus p minus s minus 1. Right, that's it. Okay. Okay, so now let's continue. I mean, the logs are sum over p prime and the logs are already showing up. So phi is already making a bit of an appearance. Okay, so let's cancel this minus signs. I have p prime and then I get, okay, so make sure I don't, so, right, so this term, there's a 1 over 1 minus p to the minus s, like twice, and there's here once, so it cancels out to becomes only once, the minus cancels with the minus, and so I have 1 minus p to the minus s minus 1, and log p, and p to the minus s, right? Right, the minus canceled with the minus, and this 2 took, right, this minus 1 took a 1 from that 2. And now, right, because this is 1 minus p to the minus s to the minus 2, right? It's written here slightly different, but it's the same. Okay, now p prime. Okay, I think we're almost there. P to the minus s. Wait, I made a mistake here. Let me see. Yes, there is, okay. So this is 1 over 1 minus p to the minus s, right? So when it comes here, it's just 1 minus p to the minus s squared, but you take one term, so 1 left, not minus 1 left. So this is 1. Okay, now it's okay. Yeah, exactly, right. So someone in chat brought up the same thing exactly. Okay, so now I can multiply the whole thing by p to the s. Okay, and now what do I get? I get 1 over p to the s minus 1 times log to the p. Okay. Okay, we're not quite in phi, but we're getting close. Okay, so let's write, let's give this a name. Let's call this cardinal, sharp. And now let's say I have, right, so I have that zeta s prime over zeta s is equal to this expression here. Okay, this is what we just showed. Okay, right, at least for s, at least for the real part of s bigger than 1. Okay. Now let's recall, right? So recall that what phi of s was defined as, right? Phi of s was, and there was something very, very similar to that, right? Was equal to log of p to the s, okay, for p prime. Okay. So, well, let's take minus phi s plus the expression in sharp. Okay, so what is this equal to? Okay, so this is equal, let me see if I can have as much as possible on the board. All right, so what is this equal to? This is equal to the sum over p prime, right? Log of p, because both of them have a log of p. And now I just have to take 1 over p of s minus 1 minus 1 over p of s, right? But, this, right, is just equal to, I mean, we can just multiply this side by p of s and that side by p of s minus 1, and you just get that this is equal to 1 over p of s minus 1, right? And so we have that, minus phi s plus that expression is equal to p of s times p of s minus 1, right? And so, I mean, another way to write this would be that, phi of s, right? It's equal to, is equal to, right? This is sharp. Now I have to do minus that expression. P prime log of P. Okay. Now, now I basically have P to the 2s, right? I mean, as this minus 1 is not really the important, right? And so clearly this converges, right? This converges, uniformly, um, absolutely, right? Absolutely, right? And locally uniform. Locally uniformly for s, for the real part of s bigger than a half, right? Because now we have, we have p of s squared, right? And so for the exact same argument as before, right? The minus 1, doesn't affect at all. I could just take, right? This is still much bigger than, say, 0.99 p of s. So I could just replace by that and run the argument with that, right? And so now this part clearly converges for when the real part of s is bigger than a half, right? And we know that zeta of s goes analytically all the way to the real part of s bigger than 0, right? So clearly is also analytic up to that pole in s equals 1 for the real part of s bigger than a half. So we have, right? So what we get from here, right? Phi of s. This is, you should have a picture. I'll try to have a picture to, because it's all, right? So you have real part. Let me try to. So we have real part equals 0, right? Real part equals a half, right? Real part equals 1, right? Now this is, so here there's a pole, right? Pole of zeta of s. Okay, this is where you can do the formula 1 over s, and you can do the product, right? We showed that we could extend all the way here, zeta s, and now we're showing that phi s we can extend all the way here, but maybe not analytically, right? All we can do is extend meromorphically, right? Because what do we know? We know that, phi of s is now equal to this logarithmic derivative minus something that converges. So this is perfectly fine. There is no problem whatsoever with this, right? If the real part of s is bigger than a half, there is no problem in this sum, right? This is fine and analytic, but this one, right, will have a pole whenever phi of s has a 0 or a pole, right? So, right, if zeta of s has a 0 or a pole, then phi of s will have a pole, And so what we can say is that phi of s extends meromorphically, right? Right? There's a meromorphic function to real part of s bigger than a half. And we know also that it has poles, right? With poles, and the poles are simple even, right? Because I mean they're just of the logarithmic derivative. With poles at s equals 1, right? The pole that it gets from, from the same pole as zeta of s, and at the zeros of zeta s. Right? So we know that zeta s doesn't have any poles here, except for the one that, right? Okay, is this clear? This is important, right? So I've defined the function here, right? I've defined now this function this way. This equation is important, right? And this is fine, right? So clearly this side, this sum, converges absolutely, locally uniform, and so on, as long as the real part of s is bigger than a half, right? Because I get basically here a p to the 2s, right? And so I just need 2s to have a real part bigger than 1. Okay? Now what I have issues is that, sure, it's a meromorphic function. This is a meromorphic function wherever, whenever zeta of s is meromorphic. And so we know that it's, besides that pole at 1, it extends analytically all the way up to here. But if it has zeros, then the zeros will be poles of phi s, right? And so this extends meromorphically all the way up to here, right? So all the way up to this, what's called a critical line. But it might have poles, and the poles are exactly at the zeros of the Riemann zeta function. Okay, and now it starts being a lot more clear what this has to do with number theory, right? Because effectively this is a way of more or less, right? Starts to be a series where you're sort of counting primes in a way. And, poles are like it going to infinity in a certain way. And so it's getting there, right? It's not quite there, but it's getting there. Okay? And maybe right here is another place to make the point that, the Riemann hypothesis implies there are no such zeros, or it says even there are no such zeros. Right? So it says the Riemann hypothesis just says that this function phi of s can be extended analytically besides the pole at 1 all the way to the real part of s being bigger than a half. Okay, so now what I'm going to show, okay, next step, and this is one of the core parts of the, of the proof of the prime number theorem. So what we'll show now, let me switch colors again. I will show that zeta s has no zeros in the real part of s equals 1 line. Okay, and this is the thing that, had many pages originally, and now is just a really slick trick. Okay, so let me see if I can show you the slick trick. So let's go by contradiction. Okay. Let's say that zeta of s has a zero of order mu, right? Mu at, okay, and we're going to show that the order of this zero needs to be 0, right? Of order mu at the point, say, 1 at s equals 1 plus, say, I alpha. For alpha, of course, a real number. okay, and alpha not 0, right? At 1, there's all sorts of issues, right? It has a pole there, we know that. Okay, okay, so let's say five S. Okay, so the idea, we're going to show that the order of this 0 is 0, but we're going to need the order of another, potentially 0, but another point, which is, let's take S equals 1 plus 2. Let me do I first. 1 plus I 2 alpha. Let's say that this is a 0 of order and U. Okay, and this of course can be, this order can be 0, meaning when the order of the 0 is 0 means the point isn't a 0 to start with. Right? So I'm not assuming that there must be a 0 at 1 plus I alpha and another one at 1 plus I2 alpha. I'm just saying take a 0 at 1 plus I alpha, and now look at the order of the 0 at 1 plus I2 alpha, but the order can be 0. So it can be just not a 0 at all. Okay? It can be 0, right? Which means that, which would mean that the zeta function is not 0 there necessarily. But we know, because they're not poles, we know for sure that these orders of the zeros need to be bigger or equal than 0, right? They are not poles. Right? Because we were able to extend the Riemann zeta function all the way to the real part being positive. Right? So they're not poles, so the order needs to be bigger or equal than 0. And what we will show is we'll show that that actually it will be exactly 0. Okay, so let's go back to our nice expression from before. Log. Oh, sorry. Okay, it's like manual copy paste by mistake. Okay, so we have this. So now what we're going to do is we're going to try and understand. Right? So we're going to try and understand the orders of the zeros by understand what the residues look at the logarithmic derivative. Right? So the idea is that we're going to look at the residues of this. Right? So the idea is look at the residues. Right? And because phi of S has only simple poles, then looking at the residues is just about taking a limit, right? We saw those examples. This is very simple when there's only poles of order 1. And so all we have to investigate is what do these limits look like? Okay, so let's do that. So we take the limit. So we're going to take the limit, right? The idea being that if we show that the pole of this at the point 1 plus I alpha actually has residue 0, then it must have not been a 0 to start with, right? Mu must have been 0. That's going to be the idea. Okay, so let's take the limit as epsilon comes from above of epsilon. Right, this was exactly how we sought to compute residues. Right, and so what is this? Right, as it's clear that the expression the sum gets cancelled out, right? Because there's this epsilon going to 0, and this part will be some finite, right? Some finite sum, right? It won't go to infinity as epsilon goes to 0, and so I just have this is just the residues, right? So I can write limit epsilon going to 0 of let's say minus. I mean, I'm just rewriting this, but it's really no need. But okay, just to make things a bit more clear. Okay, and so now we just need to look at the residues. We know that right now we know that right zeta x this has a pole at s equals 1, right? And we know it has the residue 1. Why? Because we saw that, right? Why do we know this? Because, right, we saw that 1 over s minus 1, right, was analytic all the way to the real part being bigger than 0. Oh, yeah, someone pointed out this epsilon is missing. Thank you. Right? And so once I take, right, once I look at the logarithmic derivative, then the value of this is just the residue. So the value of this is just 1. Right? Right? I mean, usually this is described as having some point S tending to some point A, right? Usually we describe this slightly different, right? So usually we write something instead like limit as S goes to some point A, and then we would do something like S minus A, right? This is how we saw it in lecture, but of course it's exactly the same thing, right? And then this would be the order, right? This would be equal to the order. I mean, if the, right, since the poles are simple, order of 0 or pole, right? And so here it has a pole of order 1, and so we get, right, we get that residue is 1, right? And like, you know, here 1 minus epsilon is my S, and 1 is my A, but everything is the same. And now we can, right, now we can write a bunch of these expressions, right? So if I now have, let me go back, right, just by, you know, calculus of residues, a bunch of stuff that we did in class, right? The limit as epsilon goes to 0, epsilon, okay, so this is 1, right? Why? Because it has a pole, right? Pole of order 1, right? If I, maybe let me write this way. Z has a pole of order 1. Okay. Now I need to put another ingredient about the Riemann zeta function, which we saw for polynomials and so on, which is, of course, you know, we have that the Riemann zeta function is the same as if I take, right, if I take the conjugate inside and above. Okay, this is also, it's also easy to see. And so because of this, if it has a 0 at 1 plus I alpha, it will also have a 0 at 1 minus I alpha. Okay. And so let's do that. So the limit as epsilon goes to 0 of epsilon. Now I want to investigate what happens at 1, say plus epsilon, right? Plus or minus I alpha, right? Needs to happen for both. Right, what is this? This needs to be minus mu, right? Why? Because, you know, exactly the same thing. If I zeta s has a 0, my hypothesis of order mu, right? This was a hypothesis, right? And if it has at 1 plus I alpha, it also needs to have 1 at y minus I alpha, okay? And, right, of course, also for the other one, epsilon plus or minus 2 I alpha, right? It has 1 at it has, then we said it has 0 of order nu, and so yes, has a 0 of order, right? Just by, you know, logarithmic derivative, the residue of the pole that gets created tells us the order of the 0 or pole of the function, of the original meromorphic function, right? We saw this in class. Okay, so now the idea is to relate these 5 terms. Okay, and so that's actually pretty slick trick. So now we relate these 5 terms in the following way. We take the sum, r from minus 2 to 2. Okay, so this, okay, so, you know, this is just a binomial coefficient because it's going to be equal to some sum. Okay, so, okay, so what do I need to write? 1 plus epsilon plus, right? And I'm taking these limits going with epsilon coming from the positives because I want to be able to, because if I do that, I can still use the summand, the infinite sum for phi, right? Because the real part is bigger than 1, and so I can still relate it to the infinite sum, which is the goal. Right? Okay, so what is this equal to? This is equal to okay, so I need to take plus r, and now I have sum over primes of log p to the 1 plus epsilon plus I r alpha. Okay, so let me move the sum inside. Okay, and I don't remember. Let's see. Inside. So now I take the sum over p of p prime, of course, of the sum r equals minus 2 to 2 of log p. And now what do I have here? Log p can come over here as well. Okay. And now I have 1 over p to the 1 plus epsilon plus I r alpha. Oh, I'm missing the binomial coefficient. Okay, let me rewrite this properly. Right, but now this is just the Newton's, binomial. Okay, p to the, maybe it's easier to just say p to the minus 1 plus epsilon plus I r alpha. Okay, and now I need to close this. Let me move the 1 over epsilon to the other side as well. Okay. Okay, just to have a bit less stuff. Okay. So, right, I'm going to take away this 1 minus epsilon. So I'm going to write log p. I'm going to write p to the 1 plus epsilon. Okay. And now I'm going to leave here the imaginary part. Minus I r alpha. Okay. And now this is just, right? This is just r alpha. So, okay, so now how do I write this? Maybe like this. Okay, now I don't remember exactly what the expression is, but I think maybe it's this. Let's check. So I take this to the power 4. I get p to the minus I 2 alpha, which is the term r minus 2 here. From here, I get p to the I 2 alpha, which is the term there. Then I get right. I get picking this 3 times and this 1 time, and I get exactly this binomial coefficient. And I get the term r minus 1, then I get the term r1 the other way, and the term r0 is obtained by getting just this twice and this twice. Okay, I think this is right. Let me just check to make sure that there's no typo. I had a typo in my notes. Yeah, this is right. Just by Newton expansion of the binomial. Okay, but where were we going? So this then is equal to log p to the 1 plus epsilon, right? Then times p to the minus I alpha over 2 plus p to the I alpha over 2, okay, to the 4. right? But because this is to the power 4, right, it must be that this expression is bigger or equal than 0, right? Because I have, log of p is positive, p to the 1 minus epsilon is also positive, and here I have something to the, right? This part is real because I have, p to the I and p to the minus I, right? And so I get to the power 4, so this must be a positive number. 1 plus epsilon, yes, thank you. Otherwise, this wouldn't converge. Right? So because I have, a number right? I have a number plus its conjugate. So this is real. Take to the power 4 is positive. This is also positive, right? So this whole sum is non-negative. Okay? But so because this whole sum is non-negative, we get an expression from here. Okay, so that, for any epsilon, this needs to be non-negative. So in particular, I get that this must be non-negative. And so what does this tell me? This tells me a relation between these numbers. Okay, and I'll finish this and then I'll finish. I just need a minute or two more. Okay, so what relation does this tell me? This tells me that, okay, I'll write it here and then we'll write it again down there, which is that, for, so we take r to be minus 2 and we get 4 choose 0, I just get 1, right? And then I get this limit, which is minus mu. So I get that minus mu is minus nu plus, right? Now I get what? I get r equals 1, right? So r equals minus 1. So 4 choose 1 is 4, right? And then I get the limit minus mu. Right? Then I get the r equals 0 choice, which is, then I have 4 choose 2 is 6, right? Times 1, right? Because that's the pull at 1. And then I get the exact same thing, right? This thing is completely symmetric. I just get 4 minus mu minus nu, okay? So I get that this is bigger than 0. Okay, so let's look here now, right? So what do I get? I get that minus twice nu plus or minus 8 mu plus 6, right? This needs to be bigger or equal than 0, right? And so maybe another way to write this is that 6 minus right, 8, yeah, it's bigger or equal than 0, right? But we know, right? We know that both mu and nu need to be bigger or equal than 0 because they're not poles, right? And so the only way this expression is 0, given that these numbers are bigger than 0, the only option, right? They need to be integers, right? And integers, of course. So we must have that u is 0, right? And so S equals 1 plus alpha I, or I alpha, was not a 0 to start with. Okay, and so we proved that this has no zeros on the line on the line real part equals 1, right? By a pretty slick argument, but using things that we've seen in class a lot, like calculative residues and a logarithmic derivative and so on. And so what we're going to prove next is we're going to use that to show that, right? And so because it has no zeros, then of course the phi x can be extended like meromorphic there and doesn't have poles there except for the pole at 1. And then we're going to use this to finish the proof of the prime number theorem on Friday. Okay, all right. Sorry for the extra couple of minutes. Yeah, I'm happy to stick around and answer any questions. Okay, so what we're going to do next is, yeah, we're going to use this to basically finish the proof. We're essentially almost done. There's going to be 2 more ingredients. One is to a certain analytic theorem that we'll prove using Cauchy's theorem, right? Cauchy's theorem hadn't made an appearance yet. I mean, it sort of makes in the background when this logarithmic derivative stuff and so on, but anyway. And then the proof that actually this v of x grows as x. Okay, so I had a couple of questions. One was why phi is a pole at s equals 1? And there was another question of about what are my research interests. I'll answer the one about the pole first, and then I'll answer the second one. Okay, so the pole at 1, right? So we have this expression, right? Was this before the last proof? Was this clear here? So is this formula clear? Oh, did I make a mistake in the last expression? Yes, I definitely did. Thank you. Yeah. So this is clear, right? Okay. So this, okay, so now let's reason about this formula again. Okay. Let me use another color. Let's go with green. So this expression is perfectly fine. Like, there's no issues with it, right? It's converges absolutely, locally uniform on any compact set, uniform, all this stuff, as long as the real part of S is bigger than a half, right? Because essentially this is like summing 1 over p to the 2s, right? That minus 1 does nothing, okay? And so this means that provided this function is okay, then the function, I can define the function on the left just exactly this way, right? This is how I analytically continuate. So what we have to understand is what are the singularities of this function. Now what we saw is if we have a meromorphic function, right? We saw this in class, in this case z of s, we can take the logarithmic derivative. And the logarithmic derivative will have poles, right, exactly in the place where, right, you always have poles at the place where there were zeros or poles of zeta s. And so this means that I can extend phi of s meromorphically all the way to the space where the real part of s is bigger than a half, because I've already extended zeta of s analytically besides that pole up to real part of s bigger than 0, right? So zeta of s is already meromorphic for s, for real part of s bigger than 0, right? Where did we see this? We see this up here. Where did we see it? Here, right? This is what we did here, right? We showed that the zeta s minus 1 over s minus 1 extends analytically to real part of s bigger than 0, right? Because this function is clearly meromorphic. I mean, it's just like the pole at s equals 1. Then, right, phi of s, zeta of s will also be analytic. It will be meromorphic, sorry, to all the way to the positive real half plane. Okay, the positive real part half plane. Okay, so now you also agree that zeta of s has a pole at s equals 1, right? There's two ways of seeing this. One is, well, if this extends analytically, right, then zeta of s is equal to this plus 1 over s minus 1. But 1 over s minus 1 definitely has a pole at s equals 1, and so zeta of s will also have a pole there, right? So zeta of s has a pole at s equals 1. Another way to see it is to just look at this sum and see that it shoots off to infinity when s equals 1. Now, that's not a very good, that's not necessarily a very good way to see this. One needs to be careful about defining the sum as the tens, but with limits, you can do something like this. Now, okay, so now this means that zeta of s has a pole at s equals 1, right? As this pole here, and it has potentially a bunch of zeros all the way in here. We don't know. I mean, we believe very strongly that this is not the case, but we don't know. Now, so now the poles of phi s will then be, right? They'll be all simple poles, and their residues will be exactly the order of either zeros or poles of zeta s. And so there is a pole of zeta s at the point 1, and so phi s will also have a pole there. And then where there's zeros of s, of zeta, there will be also poles of phi. Does that answer the question? Right? And maybe a shorter way to say it is the pole at s equals 1 comes because zeta already had a pole there. Okay, so